In this video, I'd like to work through a few problems, 3 problems specifically, dealing with hypothesis testing. And I want to focus on primarily on the individual components of the test, interpreting the problem and setting up and calculating the individual values that we need. Now you'll see down here at the bottom, there's 4 sheets. There's 1 sheet for each of the problems. So if you scroll through here, there's problem 2, problem 3, and then this fourth sheet here, charts. Well, I just put some of the important visuals that you might want to reference. So how to choose whether it's a right tail, left tail, or two-tail test, how to find your p-value, and how to state your final conclusion. So you may want to reference those if you're working through one of these problems on your own. And I wanted to cover all the bases with these 3 problems in terms of the different scenarios, when to use a z-score, when to use a t-value for your test statistic, when we're working with the proportion, when we're working with the mean, when we know the standard deviation of the population, when we don't know it. So within these 3 problems, I try to cover all possible bases. All right, so let's look at number 1. The claim is that the proportion of accidental deaths of the elderly attributable to residential falls or caused by residential falls is more than 10%. And the sample statistics include 800 deaths of the elderly with 15% of them attributable to residential falls. Use a 0.05 significance level to test the claim. Okay, so we'll start with the claim. And in this first sentence, the claim is that the proportion of accidental deaths of the elderly attributable to residential falls is more than 10%. Okay, so the key words there is the proportion is more than 10%. So symbolically, when we write our claim, we would say the proportion is more than or greater than 10% or 0.1. Okay, so once we have our claim, now we can establish the null and alternate hypotheses. Now remember, the null hypothesis is always a statement of equality. So let's use the symbol. The null hypothesis, H0, is population proportion is equal to 0.1, and the alternate hypothesis, H1, and some books use a little a instead of the 1, but I'll use H1. The alternate hypothesis in this case would be the same as the claim. Because if the claim is strictly greater than or strictly less than, then the claim becomes the alternate hypothesis. So P is greater than 0.1. Okay, so this is where you start. Express the claim symbolically. Use that to establish the null and alternate hypotheses. And now, the alternate hypothesis tells you what type of test it is, right tail, left tail, or two-tail. And since the alternate hypothesis uses greater than, it is a right-tailed test. So here is the critical region. Okay, so now let's see what we're given in the problem. And the sample statistics include 800 deaths. So we could type in an 800 over here with 15% of them. So that's your sample proportion, with 15% of them attributable to residential falls. So P hat would be 0.15. Our null hypothesis is that P, the population proportion, is 0.1. And so the complement of that is Q. That would be the 0.9. Okay? We're given in the problem, use a 0.05 significance level. So remember, significance is alpha. Significance is alpha, which means the area is 0.05. The area of this critical region is always alpha. Okay. So what is the critical value? So see how I sort of grouped these two together and these two together. Well, the significance is what you use to find the critical value, and then the test statistic is what you use to find the p-value. So I have it sort of organized in how these things are related. Okay, so the critical value, well, that's in this case a z-score. So what is this z-score? Well, we could use our, well, let's see, let's first say, if we know there's an area of 0.05 to the right of that z-score, then there's got to be an area of 0.95 to the left, and we know Excel works only with area to the left of some z-score. So the area to the left of that z-score would be 0.95. So to find that z-score, it's equal norm.s.inv. That's the same function we've been using for the last couple of chapters. So when you know the area to the left of a z-score and you want Excel to give you that z-score, this is the function that you use. Area to the left, 0.95. Okay, and we could, if we want, we could round this to a few places. That 1.645 should be a familiar critical value because we've used that before. Okay, so now the test statistic. And our formula for test statistic, which is also a z-score, is equal to the difference between the sample and population values. So that's p hat minus p divided by the standard error between those two, which would be p times q over n, and that is under the square root. So this is our test statistic, and we can just use Excel to evaluate that. So let's say equal, and I'll put the numerator in parentheses, so p hat, which is right there, b2, minus p, which is right there in b3. Okay, so that's the numerator, and then divide that by the square root, so sqrt, of p times q over n. So here's the p times the q, which is here in b4, divided by the n, which is the 800, which is right here. Now you could type the numbers in directly if you want. I prefer not to. I'd like to use the locations of the numbers. Okay, so there's our test statistic. And let's do the test statistic in blue. So if we know our critical value is 1.645, so let's label that CV for critical value. Well, our test statistic is way over here, 4.714. Let's use TS for test statistic. Now, when the test statistic is in the critical region, or the test statistic is more extreme or farther away from zero than the critical value, that tells us to reject the null hypothesis. Okay, so in this case, the test statistic is more extreme than the critical value. So because of the relationship between these two numbers, we reject the null hypothesis. That is the traditional method where you compare the critical value to the test statistic. So let's say over here, test statistic is greater than critical value, so we reject the null hypothesis. And then there's the other method, the p-value method. Now, let's actually move this a little further to the corner so I have some more room. Test statistic is greater than critical value, so reject the null hypothesis. Now, the other method is the p-value method, and the p-value is, in this case, the area outside of the test statistic. So this blue area is the p-value. Okay, and then we could use Excel again to find that area. So it's going to be equal to, now our function when we're looking for area is norm.s.dist for normal distribution. Our z-score is the test statistic, so that's this number right here. And for the second input for cumulative, we always say yes or 1. Now, this will give us the area to the left of that test statistic. We want the area to the right, so we'll have to throw in a 1 minus in front, so we take the complement of that area. And we get this really small p-value. And so that's the p-value method. So p-value is less than significant. So both of these two results, you don't need to do both. It's one or the other. It's either the traditional method, which we did first, or the p-value method, which we did second. The traditional method compares to z-scores, and the p-value method compares to areas. They're both always going to give you the same conclusion. Okay, now this is not the final answer. The final answer is some statement about the original claim. And to make that statement, you could go to this fourth sheet down here, charts, and we have this flow chart. So, does the original claim contain the condition of equality? No, it contained greater than. Did we reject the null hypothesis? Yes. So that puts us here. So the final answer is the sample data supports the claim. Supports the claim that the proportion of elderly that die due to a fall is greater than 10%. Okay, so remember this. Answering this question, do we reject the null hypothesis, yes or no? This is the step before the final answer. Okay, so let's look at problem 2. So problem 1 was a problem regarding the proportion. Problem 2 is a problem about the mean. So the health of employees is monitored by periodically weighing them in a sample of 54 employees. Okay, so that's N. Has a mean weight of 183.9. That's the sample mean. That's X bar. Assuming that sigma is known to be 121.2, that's the population standard deviation. Use a 0.04 significance level, that's alpha, to test the claim that the proportion or that the population mean of all such employees' weights is at least 200. Okay, so there is the claim that the population mean is at least 200, meaning 200 or more. So greater than or equal to 200. Now the null hypothesis, again, is always a statement of equality. Mu is equal to 200. And in this case, the alternate hypothesis, well, it can't be the claim because the claim contains equality. It's greater than or equal to. So that or equal to is preventing the claim from being the alternate hypothesis. You can't have the or equal to for H1, so we use the negation of that, or the opposite, which is less than 200. Now the alternate hypothesis, being less than, tells us it is a left-tailed test. So there is the critical region. Now let's go back to the problem and fill in these values. So we're told in a sample of 54 employees, so N is 54, there's a mean weight of 183.9, and assuming sigma is known, the population standard deviation is known to be 121.2, and our null hypothesis was that the population mean equals 200. Use a 0.04 level of significance to test the claim. Okay, so we know this area is alpha, that's the 0.04. We are using z-scores again because if you have x bar and sigma, we use the normal distribution, the z distribution, but if you have x bar and s, the sample standard deviation, that's when we use the t distribution. So we're given sigma, in this case, we're given the population standard deviation. So again, just like in problem 1, we use the z-scores, the z distribution, or the normal distribution. Okay, our critical value is this z-score right here. And so we need that z-score that has an area of 0.04 to the left. Okay, so that's again equal norm.s.inv, the inverse of the normal distribution function. And probability in Excel means area to the left. So that is 0.04. All right, so our critical value is negative 1.75 approximately if we round it. We could round it maybe to 3 places, negative 1.751. Okay, so now for our test statistic, and our test statistic, again, is in this case a z-score, and it's the difference between the sample statistic and the population parameter divided by the standard error between those two, which in this case is, for the mean, is standard deviation over the square root of n. Okay, so let's type that into Excel. So equal parentheses x bar we have right here minus mu, which we have right here in B3. Okay, so statistic minus parameter divided by, now I'm going to put parentheses around the top, parentheses around the bottom, just so order of operations works out the way it should. So parentheses sigma, which is in B4, divided by the square root SQRT of n, the sample size. Okay, so that does it for this formula down here. That's our test statistic. And our test statistic is closer to 0. Our test statistic is negative 0.972. 6. Approximately, when we round, if we want to round, again, we could round this to few decimal places, 3 decimal places, so 0.976. So the test statistic is not in the critical region. Remember, if our sample data has a test statistic that's in the critical region, then we reject the null hypothesis. So in this case, we fail to reject the null hypothesis. And again, that's the traditional method comparing the two z-scores. Now the other method, the p-value method, compares the p-value to alpha. So the p-value is the area outside the test statistic. And just by this diagram, without even calculating the value of the p-value, the actual p-value, we know the p-value, which is the blue area, is bigger than alpha, which is the red area. But if we wanted this p-value exactly, we could use Excel for that. The area to the left of the test statistic. So equal norm.s.dist, normal distribution. The z-score is the test statistic. And for cumulative, we always use 1. Okay, so in this case, our p-value is 0.164. So our p-value is larger than alpha, so we do not reject the null hypothesis. Or the critical value is more extreme than the test statistic. Again, we fail to reject the null hypothesis. Again, it's two ways of doing the same thing. You either compare these two or you compare these two. They both tell us to reject to fail to reject the null hypothesis, or the sample data is not strong enough to reject the null hypothesis. So does our original claim contain equality? Yes, it's an or equal to in there. Do we reject the null hypothesis? No, fail to reject. So this is the case where the test is inconclusive. We don't have sufficient sample evidence to warrant rejection of the original claim. Okay, so problem 1 was a proportion problem. We used z-scores. Problem 2 was a problem about the mean, but we were given sigma, so again, z-scores. Now in problem 3, like I said, I wanted to cover all bases. In problem 3, it's involving the population mean, but in this case, we're not given the population standard deviation. So a test for sobriety involves measuring the subject's motor skills. 20 randomly selected sober subjects take the test. So 20 would be our sample size, n, and produce a mean score of 41. That's the sample mean, with a standard deviation of 3.7. That's the sample standard deviation, because both of those numbers are coming from those 20 randomly selected subjects. At the 0.01 level of significance, test the claim that the true mean score for all sober subjects is equal to 35. Okay, so again, we start with the claim. The claim is that the mean of all sober subjects, the population mean, is equal to 35. Our null hypothesis is always a statement of equality. And if the original claim is equal to, then the alternate hypothesis would be not equal to. There's no mention in the problem whatsoever about more than, less than, greater than, at least, at most. So there's no mention of anything related to an inequality. Okay, so the alternate hypothesis tells us in this case, it is a two-tail test. So our area of each tail is alpha over 2. Area is alpha over 2. And alpha is the significance. So if the significance is 1%, 0.01, then half of that is on the right, 0.005, and half of that is on the left, 0.005. Okay, so those are our critical regions. Now let's go back and fill in the information given in the problem. Okay, so 20 randomly selected subjects, so n is 20, have a mean score of 41.0, let's just say 41, with a standard deviation of 3.7. We're saying that the population mean, our null hypothesis is that the population mean is 35. And the significance is given in the problem, 0.01. Okay, so we have two critical values, one positive and one negative. It's going to be the same number plus minus. But this is the t distribution. This is the t distribution because, like I said in the last problem, if you have x bar and sigma, you use the z for the normal distribution. If you have x bar and s, you use the t distribution. So we are here. Let me go back to problem 2 and circle this one because that's the one we used for problem 2. Okay, so we need these critical values, and we just need to find one because they're going to be the same number. If we find the negative one, we just use that same number but positive. So for this critical value here on the left, we know the area to the left of that is half of alpha, so that's 0.005. So we want to use the t.inv function, t.inv. And so probability is area to the left, so that's 0.005. And now with the t distribution, remember we have the degrees of freedom, which in this case, the degree of freedom is always n minus 1, one less than the sample size. So if the sample size is 20, degrees of freedom is 19. Okay, so that will give us this t-score, this t-value, because we know the area to the left of that t-value is is half of alpha, 0.005. Okay, so negative 2.86, positive 2.86. Okay, and now we can move on to the test statistic. And test statistic, in this case, again, is a t-value. But the formula is the same as before. It's the difference between the sample statistic and the population parameter. And that's divided by the standard deviation. In this case, it's the sample standard deviation divided by the square root of n. Okay, so we have all that up here. So our test statistic should be equal to, in parentheses, sample mean minus population mean. And we'll divide that, and again, I'll use parentheses on the bottom. The sample standard deviation over the square root SQRT of n. Okay, so we get a t of about, let me put it up here, positive 7.25. So that's way over here. test statistic is 7.25. So the test statistic is in the critical region. So we reject. We reject the null hypothesis. And if we wanted to use the p-value method, the p-value is the, well, in this case, the p-value is going to be 2 times the area outside of the test statistic because there's 2 tails. Let me go back over here to the charts. This one on the left is how you find t-values. What type of test is it? Left tail, right tail, or 2-tail? Or this is a 2-tail test. Is the test statistic positive or negative? It's positive. So p-value equals twice the area to the right of the test statistic. Okay. So let's see how we'll do this on Excel. We need equal 2 times. Okay, so we need 2 times the area. And that area to the right, well, we can't find that, but we could find the area to the left. So we need to use the complement. 2 times 1 minus the area to the left of 7.25. So that's T dot dist, T distribution. So the X value is this test statistic, comma. The degrees of freedom again is 19 because n is equal to 20, so 19 degrees of freedom. And for cumulative, we use 1. Oh, it looks like I forgot a parenthesis there. And we're given this in scientific notation. That just means 0.00070 zeros. So we could maybe change that to a number, and you'll see if we increase the number of decimal places, it's a very small number. Okay, so for our p-value, we get 0.0000007 about. Okay, and just like before, both of these methods, whether we compare these 2 numbers, they tell us to reject the null hypothesis, or whether we compare these 2 numbers, they tell us to reject the null hypothesis. All right, and that about does it. We could go over to the flow chart at the end if you want. So does the original claim contain equality? Yes. Yes, it did. Do you reject the null hypothesis? Yes, we did. So in this case, there is sufficient evidence to reject the original claim. So we have a significant enough evidence or sufficient enough evidence to reject the original claim. Remember, if the only way you could support the claim is if your original claim does not contain the condition of equality. Okay, so that about does it. And let me just use the same color coding I did in problems 2 and 3. So comparing these 2 numbers told us to reject. Comparing these 2 numbers told us to reject. So, all right, so this, again, just a quick overview. This, I tried to cover all the bases: proportion, mean with sigma, mean without sigma, right tail test, left tail test, 2-tail test, rejecting the null hypothesis, not rejecting the null hypothesis. So this video should be a very useful reference for the rest of the semester. Okay, that does it for this video. I hope this was helpful.